So having looked at those other videos about how pressure gauges are actually made and what's inside them, mechanically speaking, like the bellows and the diaphragm and the Bourdon tube, for example, we can talk about how we instrument these as with our various transducers. When we're talking about transducers, we're trying to turn one form of energy, like movement, into another form of energy, like electricity, for example. And in doing so, it allows us to connect our pressure sensors or our pressure measurement systems up to a computer or a microcontroller or some sort of electronic test equipment that we can record data, we can log data, we can view data and display data, and we can communicate that data. So when we're talking about transducers, we're looking at ways to get this typically analog movement, like the bellows opening and closing or the diaphragm moving, into our digital domain that we can use. And there's some fundamental ways that we do this. For example, using strain gauges, using capacitive sensors, using optical sensors, and using piezo sensors. So let's go through some of those different techniques. Now, thinking about those videos that we just watched, we saw things like our diaphragm or bellows having a small amount of mechanical movement or deflection with them as pressure increases in them. We increase pressure and the diaphragm, for example, moves up, but only by a small amount. Now, previously we've looked at strain gauges and noticed that strain gauges are a really effective way of measuring very small movements. And so what we can do is we can mount some specialized strain gauges, like these ones here, onto our diaphragm or our bellows or whatever system that we're using. And as that actually moves, because remember the strain gauge measures deflection of an object, movement in that object, we'll pick that up with our strain gauge. And so this is one way that we can use a transducer to go from this mechanical system of measuring pressure into the digital domain, something that we can use on a computer or a microcontroller, for example. There's also a few different optical means we could do so. For example, if we've got an LED, the producer's light, and a light sensor, and we have some sort of device that can interrupt the light from our light source to our light sensor, we can measure how much light we're receiving at our receiver and infer pressure from that. That's a fairly crude measure of doing so, but it has been used as pressure sensors or transducers really in the past for measuring pressure. A more accurate way of doing it is using fiber optics, another optical way where we can actually measure the position of, for example, our diaphragm based on how much light and how that light is reflected from our source fiber into our destination fiber. Here we're looking at different means of, for example, looking at the path length between those two, and also any phase change that we might have between our source of light and our received light. Another transducer that we can use to measure our pressure sensors is capacitive measures. Here we can mount one of our plates. Remember, capacitors are essentially two metal plates, and the amount of capacitance we have in those plates relates to how big the plates are. The bigger the plates are, the more capacitance, and the distance between the plates. Here we keep the plates the same physical size, but we mount one of those plates in a fixed location and one on our pressure sensor. And as that pressure sensor senses pressure, the plates will get closer together. And we can infer from the capacitance across our metal plates there how much pressure that our pressure sensor is reading. Another transducer we can use is the piezo one. Piezos are essentially small crystals that when we compress them, when we apply force to them, they produce a small voltage. Here we can mount these crystals between our diaphragm, for example, or our pressure sensor and a solid object. And when we have pressure coming in, we're actually applying force to those crystals. We compress those crystals, and as we compress those crystals, we produce a voltage. We can then measure that voltage, and based on that voltage, we can infer how much pressure our pressure sensor is reading. This table here summarizes some of the advantages and disadvantages of our different pressure sensor transducers. We see here we have different, for example, changes in accuracy, and different effects, for example, vibration that can significantly affect our strain gauge and our piezoelectric systems. We have, for example, our optical systems, which are less affected by things like electromagnetic interference or radio frequency interference, compared to some of our more traditional electrical systems. We have potential effects related to temperature changes, for example, in each of these systems, and various levels of ruggedness for each of these temperature transducer systems. So really, we need to choose a pressure sensor transducer based on the sort of application that we're looking at. What sort of data are we looking at? What sort of range is that data going to be over, like high pressure or low pressure? And what are the conditions it's going to be operating in?